I want to welcome everyone for the first meetup in 2026. Great to see some familiar faces and new ones. I want to introduce our first speaker for today. The first speaker today is Trevor Clickenbeard. He's a member of technical staff at OpenAI and works on FDB. He spent the last 9 years working on FDB at Snowflake and OpenAI, focusing on deploying, operating, and improving large-scale distributed database systems. He manages and monitors hundreds of clusters across diverse production environments. He works on performance, reliability, and operational tooling. And he's also contributed to the broader FoundationDB ecosystem through open source work and technical talks. So he's going to provide us some insights on best practices for running FDB in production. He'll cover issues and pitfalls and guidance on how to configure, upgrade, monitor FDB, and also how to integrate AI into workflows. So please give a warm round of applause for Trevor.
Hi, my name is Trevor. I'm an engineer at OpenAI, and as was mentioned, for the last 9 years at Snowflake and OpenAI, I've been working on FoundationDB. So today I want to share some best practices for deploying FDB in production, hopefully in a way that's approachable to teams that are new to FDB. So I'll first cover cluster configuration, then touch on some common issues, monitoring, alerting, and mitigation. And then I also want to touch on how AI can be integrated into a workflow to help monitor FDB. So the first question that you want to ask when deploying an FDB cluster is what replication policy to use. FDB replication policies are highly configurable, but typically the flowchart in this slide can help to guide your decision. So, do you want to tolerate a region failure or an AZ failure, or in a test case, maybe you don't even want to tolerate a single machine loss? This can guide you to one of the most common configurations. If you do want to tolerate region failure, you can use the HA configuration, which I'll cover on the next slide. So there's not enough time to cover the multi-region HA configuration policy in depth, but at a high level, mutations are synchronously replicated to the transaction logs of the primary and satellite region, and then asynchronously replicated from the satellite to the remote region. So if the primary region fails, but not the satellite, the cluster can automatically fail over to the remote region. In this configuration, cross-region communication is on the critical commit path, so avoid placing primary and satellite regions too far apart. The next key decision is what storage engine you want to use. So I can't speak to the RocksDB engine because I haven't used it personally, but I can say from experience that Redwood strongly outperforms SQLite across the board, and it was specifically designed for the FDB use case. So I'd highly recommend teams migrate away from the SQLite engine, which is more generic. Another key decision is how you want to back up your clusters. So in 7.3, there are two main options. There's snapshot backups or traditional V1 backups. For traditional backups, there's a continuous mode available to help reduce data loss on restore. And in FDB 7.4, an improved backup option is available to reduce backup load on storage servers and T-logs, which can be heavy with V1. For stateful processes, you'll have to determine whether to use local SSDs or managed disks. This is a classic performance durability trade-off with the added wrinkle that using disk with native snapshot support can unlock FDB snapshot backups that were discussed on the previous slide. Both options are successfully used in production today, so there's no one right answer. Next, operators will have to configure role counts in their cluster. This can require heavy tuning, and I'll touch on some pitfalls in a later slide. A related notion in FDB is a process's configured class. A class is a recommendation of where to recruit configured roles. So FDB offers many classes with a fitness relation for each class role pair. However, I found that it's simplest to just use 3 classes in practice, storage, log, and stateless, and then you can allow FDB the freedom to recruit stateless roles across homogeneous stateless processes. Lastly, FDB offers hundreds of knobs to configure. Most of these can be left to defaults, but a few useful knobs to override are shown here. Causal read risky gives huge performance benefits at the cost of some risk in the case of extreme clock skew. So read the documentation carefully and determine if you'd like to make this trade-off. The other knobs relate to histograms and gray failure detection, which I'll touch on later in the presentation. One common pitfall I've seen is configuring too many processes in the transaction subsystem, that is the T-logs, resolvers, and proxies. This may seem helpful to scale these roles horizontally, but it comes with the added overhead and risk. So run tests and tune accordingly, and don't provision too many. Tail read latencies are often dominated by cache misses, so monitor page cache hit rates and scale storage servers horizontally or vertically to help mitigate this. Another pitfall is not considering T-log spilling. When a T-log's queue reaches 1.5 gigabytes, it will spill tag partition mutations to disk, adding more load and decreasing the available capacity. So spilling is a fairly regular occurrence, and if your cluster isn't tested in this state, it may be unknowingly under-provisioned, and then as soon as you do start spilling, you're going to run into some unexpected issues. Next, I wanted to touch on some common issues. Some of the most common issues in FDB include rate keeper throttling, commonly from high storage queue or limited disk space, storage server hotspots, and gray failures. It's crucial to monitor and alert for these, and in the next few sections, I'll discuss monitoring and alerting. So metrics are typically derived from FDB trace events or from calling status JSON through FDB CLI. Status JSON provides some useful insights, but it's often missing data when that data is most critical during incidents. I prefer collecting metrics directly from trace events, and without native OTel support, an external tool is required to produce OTel metrics. I created one such tool, FDB OTel Exporter, which I've linked in the slides, that can be used as reference. So I don't have time to go through all useful metrics, but the metrics from these events on the slide here can provide a good starting point. The FDB OTel Exporter project that was shared on previous slides also provides more detail and examples of useful metrics to monitor. Another set of underappreciated events exposed by FDB is the set of histogram events. These expose fine-grained latency details for FDB sub-operations. For example, if you observe elevated commit latency, it's not immediately obvious what the root cause is, but by looking at these histogram events, you can get kind of fine-grained details on each of the components. Each of those green text boxes there represents a histogram that's tracked within FDB, and you can find exactly where the bottleneck is, exactly what component is slow, and that can help with mitigation of issues. The histogram events aren't easily human readable, so external tooling is required. The FDB OTel Exporter tool provides an example of how to interpolate these histograms and produce human readable metrics. Many factors contribute to a cluster's overall health, and health can't easily be compressed to a binary metric. In 8.0, I added a new FDB cluster health metric to push down health calculations and aggregations into FDB itself, exposed as a one-dimensional metric. The alternative would be maintaining many complex PromQL queries that are tightly coupled with FDB's internal logic, so it's better to maintain this logic within FDB itself. Here's an example from one of our test clusters where you can see the cluster was healthy for a while, then went into a self-healing state, and then finally degraded to a state where critical intervention was required. Once that critical intervention was applied, cluster recovered back to a healthy state. And this is much more informative than just looking at a binary healthy or not healthy metric that could be reported. Next, I want to talk about alerting. The most helpful alerts for FDB target server latency and availability metrics for FDB operations. These would include commit, GRV, and read. There's some nuance in configuring read latency alerts because you do want to alert on a single hot storage team rather than just alerting on aggregate read latency. But at the same time, you don't want to alert on a single bad server in many configurations. For example, if you're running triple replication and you have a single bad server that might have a bad disk, the FDB load balancer can automatically route traffic to the appropriate storage server. It's probably not worth waking up an on-call engineer in that case. So the read latency alerts can be the trickiest to get right. But in FDB 8.0, more fine-grained read latency metrics are reported to help distinguish between different workloads. This is because different read workloads have different latency expectations and requirements. There could be some batch workloads that are less latency sensitive, or there could be some workloads that are reading bigger or smaller keys, and your read latency is naturally going to be affected by that. Client-based alerting can also be helpful, but it can be difficult to decouple FDB issues from application issues. Choosing the right client alerting configuration will ultimately depend on team boundaries. So if the same team owns the pager for FDB alerts and the application alerts, then it makes sense to alert on client issues. If FDB is in a library that's embedded in some application owned by a different team, it may be a little trickier. You might not want to alert just because FDB client latencies are high. In some cases, it's critical to alert before symptoms hit. So alert on disk space and sufficiently degraded replication, even if there's no application impact yet. Next, I want to talk about some common mitigations. For any mitigation, it's important to consider where in the stack the mitigation should lie. Ideally, FTB could always self-heal from any issue, but due to bugs or ambiguous decisions, sometimes it's necessary for mitigation steps to be taken further up the stack. Still, it's useful to keep in mind which common mitigation should be pushed down into an operator or FTB itself. So if you're seeing, constantly getting paged for certain classes of gray failures, you may need to manually go in and exclude, which I'll talk about on the next slide. But if you see this too many times for the exact same root cause, this is probably something that an operator could do automatically, or ideally could be added to FTB's gray failure detection feature, and we can kind of remove that overhead from the on-call engineer. So as mentioned, FTB can self-recover from many issues, but sometimes external intervention is required. It should be straightforward to do the operations detailed on this slide. You should be able to exclude processes, bounce a cluster, or in a multi-region configuration, quickly shut down all processes in a region to force a failover to the remote region. To mitigate hotspots, application-level observability is critical, and application-level throttling is recommended. FTB does also provide some other tools like tag throttling and manual over-replication, but those aren't as widely used today. So definitely, some work needs to be done on the application to make sure that you're identifying where these hotspots are coming from and can help mitigate them as quickly as possible. To finish this presentation, I want to discuss some ways that AI can help to make the FTB on-call experience more manageable. I've been on FTB on-call rotations for many years, and many of my past investigations can now be heavily automated with recent model capabilities. So to start, I want to show a typical diagram of an architecture for running and monitoring FTB. Log exporters ship logs to a logs database, metrics scrapers ship metrics to Prometheus here, and the metrics database is configured with alerts that are used to page an engineer, who then investigates the metrics in the logs. And this is kind of a classical example of the lifetime of an incident. Metrics report some issue, then you get paged by pager duty, then you go do the manual investigation. But now we can add AI to the picture. So adding AI to this architecture, MCP servers can be placed in front of the metrics and logs databases, and a Codex session can be used to iteratively investigate an incident. I was surprised how well this worked out of the box when I first hooked it up with GPT 5.2 Codex several months ago. However, with each investigation, I found that a significant amount of time was being wasted rediscovering the meanings of different metrics or the schema of trace events, and Codex pursued many dead ends before arriving at the conclusion. Dead ends that, if I could interrupt it, I could have said, this is not quite the right path. You should, ignore that. It's a red herring. This is where you should generally be looking, even though it can actually do the looking much faster than I could. So with active production incidents, timing is critical, and it's important to provide Codex with sufficient context to investigate quickly. This brings me to my next slide, where Codex skill is given access to FTB source code and the alerting configuration, as well as cache context on the most important logs and metrics to investigate. So using this skill, production investigations have sped up dramatically. Also, recent model improvements with GPT 5.5 have made Codex far more intelligent and autonomous, allowing it to investigate very complex issues, the kinds of issues that could take me hours to do previously. FTB can come up with, or Codex can come up with some pretty creative solutions to problems. So how can you set up a similar skill? Codex provides a built-in skill creator skill, which can be used to create skills for FTB debugging. Codex sessions shouldn't waste time determining trace events meetings, so a one-time investigation can be used to cache this information. So this was motivated by Evan from Snowflake, suggested that I give a prompt like this. Analyze all distinct trace event types from the last hour, find the corresponding code, and save explanations of the trace event schemas and each field's meaning. So a few minutes later, Codex came back with an analysis of what all of these different trace events mean, how to interpret their schemas, and where to look in the source code to identify why they might be showing up. So this has helped to speed up Codex investigations significantly. And finally, another thing, you can provide templates for useful queries. So if you know that investigating cluster recoveries is a very common use case for any investigation, you can cache some queries saying, this is how you investigate what stage of recovery the cluster is at, and Codex doesn't have to rediscover that on every investigation. Finally, as new issues are encountered, Codex will discover new exploration paths not previously attempted. Ask Codex to update its investigation skill accordingly, and this will save time on future investigations. Thank you. So it looks like it was under time, under 20 minutes. So I have time now for Q&A. If anybody has any questions. Yes? No, that. Oh no, this was the prompt given to Skill Creator, and then Skill Creator created a much more complicated. So then Skill Creator creates the skill, and there were other prompts involved too. But one of the files within the skill is a markdown file describing what every individual trace event means, and that was created by prompting Skill Creator with this prompt. No, actually, so a lot of it is tied to our internal kind of metrics architecture, so it wouldn't be helpful to share online. But actually, I think this process was so easy that there wouldn't be much value in sharing it online. Really, if you ask it to create a skill to help investigate FTB incidents, basically share this slide and say, Codex, build me a skill based on this slide, it will do it. Yeah.
Question about running FTB on operator versus VMs. In OpenAI, do you run it on VMs or on using the operator? And
yeah, so we don't use the Kubernetes operator, which is part of why I didn't touch on that in this presentation. So we run on VMs.
Okay, was there a specific reason for that decision, like to not use the operator?
So one of the issues that we've encountered with the operator is frequent restarts of processes, which can trigger recoveries. When pods are recycled, it would harm our availability targets that we want to meet. Another issue is the non-stable IP addresses. So I'm sure companies that have more experience with the Kubernetes operator have tips for kind of working around those issues, but we have our own operator, not the Kubernetes one.
Yeah. And can you also talk a little bit about doing upgrades? Like, what's your process for doing version upgrades on FTB?
Yeah, so one key thing to remember about upgrades is it's necessarily going to require restarting processes. And this is something that I cut from the presentation, but I probably should have covered. For patch releases, there's protocol compatibility, which limits what you can put into a patch release, but also means that you can do a rolling upgrade. Even though a rolling upgrade is supported and maybe recommended for storage servers so that you don't refresh all of the page caches at the same time. For stateless processes, every time that you restart a proxy or a resolver or the master, you're going to force a recovery and have some unavailability. So if you do a rolling upgrade of all of your stateless processes, you're going to have more downtime than if you just restarted everything atomically. So my main guidance would be to do an atomic restart of all of the processes in the cluster. And then for minor or major upgrades, you lose protocol compatibility. So there, it's even more critical to just upgrade everything all at once, even storage servers.
Hi, I have a question. Thank you so much for the sharing. It's really inspiring. So I'm just wondering, the example you gave to how to integrate with AI, for me, it looks like we apply some AI intelligence on top of FTB, like how to debugging or troubleshooting to release efforts on engineer. But I'm thinking of FTB itself as a storage layer. In this word agent or this kind of idea becomes so popular, is FTB possible to be some as a storage perspective to be integration with agents, let's say agents backend storage or something, to put some efforts there? I'm not so sure, just thinking aloud, just want to know your opinions.
Yeah, so yeah, it's kind of orthogonal to the production investigations of FTB itself, but definitely I think there's a lot of potential there. We were actually just discussing this before I came up. There was a side discussion where people were discussing how FTB can be, because it has such a minimal interface where you just have this distributed, or you have a transactional key value store, but no schema imposed on you, it can be a bit intimidating and difficult to develop on. but it provides a lot of really nice fundamental primitives for development. And agents are smart enough to understand this simple interface and build all sorts of complexity on top of it. So I think FDB can be a great foundation for a lot of agentic workflows as well.
Oh, thank you. I have another small question. It's like, actually, we have a use case for utilizing FDB transactional version step as a whole system watermark. It's like to enable the system level data lineage tracking. Just thinking of like a case like we have multiple FDB clusters in different regions, and actually we want to achieve a globally data lineage tracking with this FDB transaction version step. Then we need to manage the different discrepancy between different clusters. So the way of how we achieve it is we will use the FDB advanced version stamp to bridge the gap between different clusters. And so far, during our POC, we didn't see any concerns. Thinking of like any past experience or any opinions or any insights against this kind of scenario?
So originally, version stamps were not really meant, they advance at 1 million versions per second, but they're not directly a good proxy for microseconds because, for example, when a cluster goes through recovery, it will just bounce the version by 100 million versions, and there's internal implementation reasons for that, but ultimately, it's considered a safe decision because you weren't meant to depend on versions as a clock or keep them synchronized across clusters. There have been other use cases, though, similar to yours, where that that assumption has kind of been relaxed a bit, and we want to, compare version stamps across different clusters. So yeah, definitely, it's something that other teams have explored. It's a tricky problem to get right because you can have, because the feature wasn't originally developed with this in mind, and there can be skew in clock speeds across different clusters or the number of recoveries that different clusters go through. But there's definitely a lot of value in keeping them in sync. I know other companies have seen similar challenges.
I see. Okay, thank you.
You talked a bit about casual read risky.
Yeah.
You recommend it to be on by default.
Yeah.
Can you talk to a bit of the caveats there and when can it be dynamic?
Dynamic in that, yes. So there's a knob that will allow you to basically, at the proxy level, you set this knob on the GRV proxy, and it will always use the causal read risky algorithm. You can also set a client option where the client says, I'm okay with this, and then the GRV proxy knows, okay, for these transactions, they're okay with using the causal read risky algorithm. So it is dynamic in that sense. What it is essentially doing is avoiding a read on the GRV path from the GRV proxy to a quorum of transaction logs. So the safest thing to do, every time you get a read version request, you have to validate that the current generation is still alive to avoid a split brain problem. But there's a lot of overhead in every transaction or every get read version request having to sync with a quorum of T-logs. So to avoid that, you kind of do that read in the background only once periodically, and it removes a lot of performance overhead, but in a case of extreme clock skew, it could be that you get a read version from a previous generation and then you break FDB's linearizability guarantees.
Yeah, just to add on, it would have to be clocks that are going at different clock speeds, not just absolute time difference. It's not like an NTPT error or date time would get it wrong. It's like the amount of time that you're measuring a lapse would have to be dramatically different. So it's actually extremely not risky despite the name, but you should read the documents. Like it's effectively, for this to be a problem, the amount of time a recovery takes, that's what has to be compared with your polling interval for how often you're batching these requests on the GRV proxy. So you can look it up, but it's in general, I think pretty much every person who's ever like actually looked into it has deemed it not risky and gone ahead and done it.
Thank you.
Since the question hasn't come up yet, I'll ask, what's the use case, or how do you use FoundationDB at OpenAI?
So it's used for internal metadata storage. Yeah, I can't go into too many details on what the metadata is stored for, but like many other companies, the traditional use case for FoundationDB is for metadata storage. Yeah.
Any other questions in the room?
Have you considered, or do you use any other distributed key value store like TyKV or TyDB?
No, so at least, yeah, no, we don't use, we're betting pretty hard on FoundationDB, and yeah, FoundationDB is kind of, for this class of workload, FoundationDB is our go-to tool.
One last question. FDB is very well known for using deterministic simulation testing thoroughly. How do you test at massive scale? Because these single-threaded runs, they don't quite work for, let's say, 10,000 nodes and so on.
So we set up Joshua. So Joshua is the open source tool maintained by Apple that is kind of the go-to tool for actually using FDB as a task queue for testing at a massive scale. And then it comes with this Joshua agent scaler, which you can run in Kubernetes, and it can scale up to a very large number of cores. So we run hundreds of thousands of tests every day, through Joshua, and it's been a great experience. I know other companies have also used Joshua regularly. So I think everybody who tests FDB at scale with simulation testing relies on this Joshua framework.
So does Joshua provide deterministic simulation even at that scale?
Yeah, so FDB itself provides the deterministic simulation testing. So if you take the FDB server binary and then just run it with like the simulation rule, it will simulate an entire cluster inside of a single thread and give you deterministic simulation testing. But then to run hundreds of thousands of those, Joshua is the tool that will spin up hundreds of thousands of those processes and aggregate the results and report that. So FDB itself actually provides the deterministic simulation testing. Joshua is just a harness.
I think he's wondering about like cluster scale testing stuff. What do you have anything you want to say about that?
I see. So you're talking about like an individual FDB cluster running with hundreds of processes. Yes, so inside of there is a size limit for the deterministic simulation testing. You're not going to run thousands of processes inside of a cluster there. So there we have to test on real clusters. But a lot of it's the same problem in a lot of ways, just kind of scaled up. And I have seen issues in the past that weren't caught in simulation because when you're running with hundreds of storage servers, you run into a particular edge case that you wouldn't catch in simulation. But I'd say for the vast majority of cases, you can reproduce the issues, with the intense chaos testing that we do in the deterministic simulation testing. You can catch the class of issue on a much smaller cluster. And then to get confidence with a 1,000 process cluster, you do have to, leave the simulation framework.
Yeah, so this topic of release qualification and release velocity, like this is a thing that we're thinking a lot about at Apple, and like it's a thing we're working on. But I don't know. I don't have details to talk about. But it is a big enough difference in number is a difference in kind, and sometimes we see interesting stuff, and it's an area of active work. Put it that way.
Do you use antithesis anywhere in your stack, either FDB or elsewhere?
So FDB, the same people founded Antithesis and FDB, and a lot of what Antithesis provides is like bringing FDB's simulation framework to software that wasn't written directly against a simulator. So in a lot of ways, there's not as much benefit for FDB to use, and we don't use Antithesis for FDB, and there's less benefit.
Beyond FDB,